So, the problem that we set out to solve is the fact that cloud enables you to provision storage and compute power, but not database services until now. And what we mean by that is that database services, particularly in a shared nothing architecture, are very much tied to a physical computer, and hence the local disk and all of that. And what we do is we enable it to be much more easily virtualized, which makes it much more cloud-friendly, as we'll explain shortly. So, and what we're doing is we're working with open source databases to cloud enable them. We're starting with MySQL, of course, and making them easier to provision, scale, maintain in the cloud. So we see this as a very interesting disruption because in the early days, or I should say earlier days, the comparison between shared nothing and shared disk was a rather simple one. The reason being is that with CPU advancements far outpacing the disk advancements, the CPU was really traditionally or typically starved for information, and the bottleneck being the I/O. So when you're looking at shared nothing, when you have a local disk and you can get 64 megabytes per second into your CPU, that's a great performance advantage. When you compare that, and this comparison here is to regular Ethernet, but even with fast Ethernet, you'd be looking at only 12.5 megabytes per second to the CPU. And so as a result, the shared nothing option had much better performance. On top of that, shared nothing is built on low-cost, commodity servers, and so it therefore had a cost advantage as well. So anytime you have both price and performance advantages, it makes it pretty much a no-brainer to go down that path. And so people did. And so shared nothing became the predominant platform. And people then realized that as they get more and more data or more users, they need to scale up. They have to partition their data into multiple servers. And of course, if one of these goes down, you need to have these slaves to back it up. And so people were willing to jump through these hoops imposed on them by shared nothing, again, because of the performance and cost advantages. Now, what's happened is, the high-end storage has become very, very efficient at pushing data through to the servers. And now this is not just for shared disk, this is also for shared nothing, but the ability to push 200 to 400 megabytes per second over the line to the servers makes it much more of a level playing field when it comes to performance. However, obviously the shared disk option was a lot more expensive. However, cloud is now changing that because in a cloud environment, we're able to amortize the capital investment in the big SAN and all of the interconnectivity and all of that, and amortize that over a large number of companies, and therefore drive the cost down considerably.
So is that the shared disk there? Is that Oracle's Exadata offering there? Have you heard of Oracle's Exadata offering? They announced it last year. It was their big shared disk storage, huge monster or whatever. So that just the picture on the right there of the shared disk reminds me of Oracle Exadata, which they're probably going to throw away now that they bought Sun.
Yep, and Exadata was actually a combination of shared disk, high-end interconnects, I think using InfiniBand, and then the server. So it was basically a full rack solution that had all of that in one. So you could kind of just roll it into a data center, and it was all tuned for shared disk implementation running Oracle RAC. But yes, that's one of the implementations that one can think of when thinking of high-end shared disk. But also we're seeing a lot of things, for example, from coming out of EMC, very high-end SANs that are pushing a lot of data, and they're able to basically level the playing field with regard to the performance aspect. Obviously, we take advantage of two of the top 10 disruptive technologies according to Gartner, which are cloud computing and virtualization. So we look at this and we say, okay, so this change, the underlying physics, basically leveled the playing field, both on to some degree on a cost basis, but certainly on a performance basis. And so you were no longer then kind of pigeonholed into the shared nothing, so you could look at them in a much more comparable way. So what we do is we extend the open source databases, starting initially with MySQL, and we enable them to operate in a shared disk cluster. And so what we do is we have a centralized lock manager, and that coordinates the buffering, recovery, locking, things like that. And then each of the nodes, in this case we have a 5-node cluster, all have direct access to the data. And so they operate in a shared disk environment, much like Oracle RAC, with full access to the data. So what does that mean? Well, let's walk through some of the advantages of the shared disk architecture. So one is if you have a failover, you have high availability because instead of partitioning that data and having the master slaves and all of that, all of those nodes there in the cluster have full access to the data. So if one node goes down, the others just keep running. And so, very much a high availability solution. The other nice thing is cluster level load balancing. So when you partition into a shared nothing environment, then all of the disk requests or all the database requests have to go to a particular server or its slaves. And in a shared disk environment, you can use any one of those servers. So what this does is it supports much more dynamic or fluid environments. So for example, let's say you have, let's say like a lot of logins in the morning. Well, instead of running those all through your login server, you can spread them out so you might have 5 or 4 of these 5 servers running logins in the morning. And then, as the day progresses and the workload progresses, it's able to basically load balance across the entire cluster. Another nice advantage is that there's no need to partition, set up slaves, set up replication. You're working in a master-only environment, and all of the data is being served from a single trough of data, in this case from a high-end storage. The other nice thing is that you have data consistency. Because you don't have multiple copies of that data, it is consistent. You're not running into stale data and the problems that can create. So these are some of the more significant advantages of shared disk clustering. Now, the other interesting one is virtualization. And so I have a little kind of animation here to show you what we mean by that. So in a traditional MySQL server environment or MySQL environment, you have the MySQL database with a storage engine working on a local disk. With ours, because you have shared storage, you can run multiple VMs. So you might start with one, and then as your load increases, you add additional VMs. You can add additional servers for failover, things like that. You can move your VMs. As your usage drops off, you can scale down. So the ability to dynamically scale both up and down in terms of loads in the cluster without having to worry about things like shutting down the application, repartitioning, redirecting the database calls, things like that. It just dramatically simplifies the entire process. Now this is our internal architecture. And so I've noted Ingress and Postgres, those are kind of future plans. We don't have a firm roadmap at this point. At this point, we are supporting only MySQL, and then also applications written directly to our API. But that is an open API, and anyone can use it to write to our storage engine, not just MySQL. Underneath that, we handle all of the indexing, recovery, storage, all of that, and most importantly, the lock management. So we coordinate all the lock managing with all of the locking with a central cluster manager that ensures that we're not having two nodes writing to the exact same data at the exact same time. The customer value proposition is that it runs on low-cost cloud infrastructure. So unlike, for example, Oracle RAC, we can run on the Amazon infrastructure. We do all of our initial testing on Amazon. The other nice thing is the high availability, as I addressed earlier. It is dramatically easier to set up in terms of you don't have to do the partitioning, the slaves, replication, and of course partitioning is a big part of tuning as well, so tuning is much easier. The long and short is that over the years, the costs of both hardware and software particularly driven by open source solutions, those costs have gone down significantly. The one cost that has not dropped is the cost of services. And so by making the database much easier to set up and maintain and tune, we're enabling a lower total cost of ownership because we reduce the services required to manage this, which again is a very critical thing for the cloud where the whole idea is centralized services that they can deploy across the group.
Mike,
which brings us to
I have a few questions. If you can go back to the previous slide.
Sure.
And hopefully you can hear me well. Before I was kind of walking around the room and shouting, so hopefully I'm closer to the thing now. You can hear. So a question about running on like low-cost cloud infrastructures like Amazon. Are you using something like the elastic block storage for that kind of shared space, or like how does that work?
Yes.
Okay. So
yes.
Okay.
We're currently running off of EBS. We run EBS to an NFS server, and then that spreads it out to all of the various nodes.
Oh, great. That was going to be my question too. Is what if there's no way to share all the stuff? Like Amazon, it's pretty easy, but other I don't know about other cloud infrastructures. Like if Mosso, it's just as easy. But if you're running it with an NFS server, then it's easy enough to do on almost any cloud computing infrastructure.
Correct. Correct. Now, I mean, in terms of performance, you're going to get what you pay for. So, the higher end systems are going to have better throughput, better performance. And then, as you scale down to pizza boxes, your performance will drop off accordingly. Our understanding is, although Amazon is very tight-lipped about their plans, we have heard that they are moving towards a multi-attach EBS, which would eliminate the need for NFS, which would be ideal for us.
Right, but just in case, I haven't worked much with Mosso, and I've worked a little bit with AppNexus. Those are some other cloud computing providers. Mosso is actually Rackspace's option. I don't know how they deal with this issue. Like if Rackspace could do it easier or not with Mosso or AppNexus or whatever. So, but the ability to run using NFS makes it so that it can run on any cloud computing pretty much infrastructure. So yeah, it would be beneficial if Amazon had a better one, but even if they don't, that's fine.
Yes, and so in the cloud world, there's a couple of options. One is, as we mentioned, with EBS and NFS, and then that allocates it for all of them. Others, you can work with a NAS storage, so that it might allocate some portion of their high-end NAS, which is getting very, very cost competitive these days in the cloud. And then NAS basically is an NFS interface, so no problem there. And then with a high-end SAN, they might, someone like a Rackspace or Mosso might allocate SAN access where you have shared SAN, and it might use a Red Hat GFS or a Veritas cluster file system or one of these others that basically gives shared access to the data.
Great. Are there any other questions before we move on? Yep.
company that I work has patient information. We're very concerned about the security of our data. Does he support either fully encrypting any data that's stored on the cloud? Because that's the thing that makes us nervous, is that we put something out on the cloud and it's not encrypted.
Right, and anyone can look at it. So I don't know if you heard that question, but basically somebody works with patient data that is sensitive information and wants to know what kind of encryption is available and how encryption is supported in the cloud, specifically with something like ScaleDB. Because if they go and put it on like Amazon's cloud, because it's a shared IP and all that kind of stuff, he's interested in if there has been work from ScaleDB into that kind of arena of data privacy and security on the cloud.
Or just how would he handle it?
Right, or how would you handle it? I mean, it's not necessarily, is it a ScaleDB thing, because ScaleDB is for scaling, not necessarily for encryption, but is this a problem you've run across with your client, with your existing customers, and how have they dealt with it, or how would you deal with it?
Still there? Oops.
So, hi, this is Moshe. I'm the CTO of ScaleDB, and we currently in the first version, we don't have anything special for security. This would come up in the second version. We could use basically any type of encryption on the data. But the first version, which is being tested and is in a beta phase, does not have that feature yet.
So it would be however you would normally do security with MySQL or the other databases at this point. But it is something you're looking into.
I mean, we currently, what we do is we store the data that we get from MySQL and receive the data that MySQL needs as any storage engine. But the idea is to add at some point encryption to the data, so if somebody tries to hack the data itself, then you would have to go through the encryption layer.
Okay, great. That answered his question. Any other questions before we move on? Okay, great.
All right.
Yep, we're good.
So the value proposition for cloud vendors, one of the important things for the cloud vendors is that they want to move people from a specific hardware lease agreement to more of an SLA model. And the reason they want to do that is because A, they want to allocate things like storage and the like, and B, if you're signing up to lease a dedicated server, there's no cost advantage for them. Whereas if they can allocate your services under an SLA across their infrastructure and do so in a much more flexible way, then they can share it across larger numbers of people, and they can give you a much more competitive bid as opposed to simply, co-locating your server or something like that. So from their perspective, it's very important to shift people towards an SLA or service level agreement type mentality. The other interesting thing is the fact that we are compatible with virtualization. The separation of data and computing supports all of those things that I was talking about in terms of the flexibility of moving them, or sharing, spreading that service across their infrastructure. The other thing is that we significantly reduce the management overhead. Now, from a cloud manager perspective, like a Motto or others, even though the end user is responsible for their partitioning and tuning and things like that, if they run into problems with performance, even though it's tied to their own tuning or partitioning, they're going to pick up the phone and call the cloud vendor, which creates more costs, more overhead for the cloud vendor. So the fact that this is really a low-touch solution, very simple solution, and that it dynamically addresses any changes in application usage and things like that, makes it much easier to support in the cloud.
Great.
And that said, I would invite everybody to join our beta program. The things that we are ideally good for are large data sets and transaction volume, indexing across large, long keys, and also complex joins. Now, I didn't get into a lot of the detail on our indexing, but we have a unique indexing approach that makes us very good for joins and long keys. And so the way to join our program, our beta program, is to go to ScaleDB and just click on Try It Now, or just go directly to the URL at the bottom. So any questions?
Do you have like an online demo or anything, or it's really, because it's just kind of behind the scenes in Magic, so it's kind of hard to have something like that?
You know, I wonder if I could pull someone up to. I don't have it on my machine. We do have a running demo where we run, I think it's like 10 nodes, and then we dynamically scale up and down. I could go and see if I could grab someone to show that real quickly.
Yeah, if you can.
Would be of interest?
Yeah, I think would people be interested in seeing that, because it would be interesting to see. Okay, you can really do it in one command with like, hey, ScaleDB add machine or something like that.
Yeah, I think the demo is running on Amazon. Let me see if people are around.
Sure. Anybody else have any? Yeah.
I mean, I can wait.
Yeah. Well, why don't you ask him, and we can.
So I'm curious what kind of, I mean, there's some mention here in terms of what workloads, but in terms of their testing, what kind of benchmarks or workloads they test with, and how much faster are they on those kind of workloads, and maybe what kind of workloads might be not ideal for this kind of system?
Gotcha.
Some of my experience with Oracle RAC is that you run into issues where you've got tremendous bandwidth to SAN, but if everybody's looking for the same few disk pages, you can really run into hotspots that can kill your performance.
Right. Okay, Mike, let us know when you're back.
If he's
Okay.
away, how can he hear you
I
say
think
that?
we need to switch the presenter
Uh-huh.
so we can do that. So hold on just 1 minute.
Sure.
Okay, let me just send him an invitation.
Come on in.
Hey, across the rat maze.
I'm typing the question in, so taking a while.
Process sounds over.
All right, so I just typed a question into the chat, which is a question about workloads that somebody brought up, and basically, what are some examples of ideal workloads, or maybe perhaps some non-ideal workloads, and that the Oracle RAC isn't particularly good if there's a lot of queries that are accessing the same 2 to 3 data pages, and is wondering just if ScaleDB has that same behavior, or if it behaves differently, and if so, how, that kind of thing.
This is Moshe. So the way that the engine is designed is basically to work against OLTP types of applications. OLTP application would be ideal, although because of the clustering, we find a lot of interest from many other different types of applications. And at the end of the day, it's really about testing and trying to find if it's very hard to, very difficult to define in advance some rules, because all the applications behave very differently. So really about just downloading the software and trying.
Great, I think we're getting some feedback from the second presenter, so if one of you can turn off your microphone.
Turn off your microphone.
I can try that.
So I think I think you need to shut down your speaker.
Yeah, there's a little icon on the control panel, like on the very left-hand side of the control panel. You'll see like.
You're muted.
I know I'm muted. Oh, I'm muted. Thank you. If you look on the left side of the control panel, there's a little mute button.
Yeah, we got it.
Okay, never mind. Thanks. I'm like, I know I'm muted. I'm trying to tell them how to mute. Oh, that was great. That was classic. Thank you, guys.
I know I'm muted.
I guess I was also really interested if they're running any particular benchmarks or have a kind of a suite of things that they run to test their internal performance, and if they have a sense of how that's going.
Yeah, they also have, the question is also is how's the benchmarking going, which is probably the question you get all the time. And what's the sense of the performance, the performance benchmarking that you guys have done and that kind of thing. And if there's, again, any particular workloads suited towards it, or if it's like, oh, all workloads except this kind of workload, that kind of thing. Just to kind of help better evaluate why it's, why it's good.
Okay. Unfortunately, the person who would answer that is Moshe. He's just in the process of firing up his machine right now.
That's all right. We won't forget to ask that, so I can type that into the chat. So benchmarks, because you already said OLTP workloads. So I have it muted now, but somebody was saying Green Plum before, which is apparently data warehousing. So this would kind of be probably an analog to OL to transactional.
No, I think we're OLAP.
Yeah. So if you're OLAP, then this wouldn't be. Which is interesting because he did say it was for complex joins. So how could it be for? It's for complex joins, but not really complex joins.
Represent. We'll find out while I talk. But the idea here is that what we see here is 6 nodes running. So every square that we see represents a node, and the bottom line represents the overall throughput. But let me just 1 minute to find what is the write-up on the background. We'll fix it and then continue.
Okay, so this is the throughput, and each of these 6, which it's not really refreshing here, each of these 6 here are machines.
See what's going on?
And I don't know what I guess the addition of all of these is this
Sit on the
number
remote.
here. So this says like 155.8, 121.1, 104.8, 127.9. This says 800.2, 799.9. So I'm guessing it's some kind of count of how great it's doing or something.
So it's just a problem with the resolution of the screen, so we're trying to fix that, and it'll take us a minute, and then we should look at the demo.
Great. What are the numbers next to everything?
So what we see while somebody is fixing it, what we see, every square represents a node in a cluster. So this demo brings up to 12 nodes on Amazon EC2. Every square represents a node. So we see node 1 up to node 12 on the screen. And the bar inside each square represents the throughput. We can see also the number on the right side next to each square that represents the node. The number, for example, 95, 81.8, those numbers represent those throughputs at this particular node. So every node has its own throughput depending on the strength of the machine and the process which is done in the node. And the bar on the bottom represents the overall throughput, which is obviously the aggregate of all the processes which are done in all the nodes. So as we can see, as we increase the number of nodes, the overall process increase. And from our testing, at least in this particular benchmark, the growth of the throughput is almost linear. And so the idea is this: you could put your data set in a shared disk environment. It could be either a public or a private cloud. So you have a shared disk, and you could pull up nodes as much as you need. And if you need to increase the throughput, you could obviously bring a new node that would share the same physical data and allow you to execute more operations at the same period of time. And that's one of the main features that ScaleDB, that the ScaleDB engine can provide to MySQL.
Great. So are those numbers like queries per second or amount of data? What do the numbers actually mean?
I think that those are queries per second, but I'm not 100% sure because I didn't write the application. It represents the amount of work per second, but I'm not sure what the amount of work stands for. I think that this benchmark is Sysbench, which is a benchmark that many of the MySQL users are using.
Yep, and with the bars there, is that actually proportional? Like it looks like we're at about maybe half or 2/3 of the total throughput. So does that mean that the total throughput is actually when the bar gets to the end, or is that not like relative or?
It's the actual throughput on each node. The bar inside each square represents the throughput in transactions per second or operations per second per each node, and the bar at the bottom represents the aggregate. And the fact that it flashes, it's because it runs on Amazon EC2, and we refresh the screen. We test, we monitor each node every second or so to see what's the throughput that this node is executing, and we get the result and present it with those bars.
Okay, but I'm looking at the total throughput bar, for example, and it looks like it's about 2/3 of the way to the end of the box, right? So it fills 2/3 of the box, and it's at about, say, 1100, whatever. Does that mean that, let's say it was 1200, does that mean that the max capacity of this whole thing is, say, 1800?
Well, with 12 nodes. I mean, if you want to go beyond that, then we need to pull up another node.
Right, but it does have a sense of the maximum capacity of the system as it is right now. Obviously, if you wanted more capacity, you could add more nodes, but I was asking for capacity planning, right? Because if we know that this is the capacity, and then next week we know we're going to have 1500 queries per second, then we know that we can still handle that.
Yeah,
but
those
maybe
nodes are not being heavily used.
Yeah, it wasn't
Doesn't
done.
look like they're being heavily used at all.
So there are different ways to scale that. So one instance, we can measure how many connections, how many MySQL connections are available,
That's why I'm asking.
and pull up and down
Like,
nodes.
a bar
and
doesn't make any
double
sense.
load on it,
Connections
change
which
the
are
scale of
available.
the
Another
Yeah, I
way
think so too.
to add and remove nodes is by CPU usage. So we can test the different nodes to see what's the CPU utilization on each node, and that would trigger a decision whether to bring more nodes or remove nodes. Or you could simply know that you need that many nodes and just keep it like that. So if this throughput, overall throughput is not enough, then you would know that 12 nodes are not enough for you, so you might need more nodes.
Great, and
So there are different.
Great. It sounds also in there that you were saying that the load balancing can be tweaked a little bit. Like you could actually tweak the load balancing instead of, say, doing round robin where each one gets a query, that you can kind of fudge it so that it's based on a different, it's based on CPU load or something. Is that correct?
You can. I mean, so one of the things with a shared disk is that we can send a query to any one of the nodes because they are all masters, they are all equal. And we don't do that, but on the application side, you could definitely send queries to a particular node if that's what you want. We don't manage. We do just the storage engine. I mean, we use any routing structure that you would want to use. We don't care.
Okay, great. Is there any other?
Did I answer?
I'm just curious, is only one of those read-write? Because I mean, I'm just what the letter next to it, they're all RO, but it's WR on the last one.
Great
so.
question. Yeah, that did answer my question, thank you. We're noticing that only node 12 has WR next to it, so does that mean that's the only read-write node?
Right. In this benchmark, there is only one writer, and the reason is that it's not because of ScaleDB, it's because of the sysbench. The sysbench benchmark is something which is being used by InnoDB and other storage engines which don't have a cluster that can't work in a cluster. And what happens is that if we have multiple nodes running, and all the nodes, there is a lot of contention that is happening because it works with many nodes trying to update the same block, and the type of error that we return, or the type of error that is returned, makes the sysbench test to stop. So what we need to do is either modify the sysbench a little bit so that it would consider those errors, or use a different test. But we wanted to use something which is standard, so we didn't want to get, we tried to avoid multiple nodes trying to update the same block at the same time, simply because the sysbench assumes that everything goes through, there are no conflicts.
Great.
So there is a problem similar, like if you try to access the same page or something, there is a contention over there.
Right. So the question is, one of the questions we had, Moshe, while you were setting up the demo was, is it like Oracle RAC? Because with Oracle RAC, if you're trying to access the same data, even read, right? If you even read, if you're trying to access the same one with 100 different people, then there's going to be some contention issues. And so the question was, does that still happen? And it sounds like it does. I mean, it's hard not to do it when you're scaling, right? Because if you have a shared disk, then there's only so much that can access that disk at one time. But so it's not necessarily a failing of ScaleDB. It's just how the architecture works. But we were wondering if there's any difference between Oracle RAC with that kind of issue.
So the way it works is when somebody wants to read, he's asking for permission to lock that particular disk page or row for read. And if he does that, then it doesn't prevent from others to read. So we can have, I mean, if we remove the writer, then everything would be everything would work even in a better performance, because there wouldn't be conflict between the writers and the readers. So if like 1,000 users wants to read the same piece of information, there isn't any issue with that. They can all go ahead and read it. The problems are, or the difficulty is when some people want to update the same piece of information at the same time, some other people want to read it. Then there are conflicts, and our log manager, we have a cluster manager, takes care of it. But the cost of that could be that if I'm updating something and I've locked it and I'm using it for a long period of time, then others can't use it. Simply they have to wait until I finish my process. So to answer your question, if everybody is reading, there isn't any issue with it. If some are reading and some are writing, then they go into a queue, and we resolve the process by somebody updates. We've got to wait until it finishes to update the growth.
Okay. Now, if I were to say, if somebody, let's say, wrote an article in, I don't know, like DB World magazine or something like you see all the time, and they said, ScaleDB, it's Oracle RAC, but for open source databases. Would you say that's accurate or not accurate, or how would you say that's a fair comparison, or that you do things a lot differently, or?
I mean, there are lots of similarity. I mean, it's in terms of the functionality, it provides a very similar functionality. So in that sense, it's a fair comparison or a fair statement. In terms of how it's implemented, there are some differences. I mean, there are some things which are similar. There are some things which are different. I was working on this architecture of ScaleDB with a guy named Vern Watts, who used to be the chief architect of IMS, which is the database, IBM's database on the mainframe. And I worked with him on that for 3 years. Unfortunately, he passed away a few months ago, but the basic design is more similar to the database, IBM database on the mainframe than to Oracle. But in terms of the functionality and what we try to deliver, it's pretty much the same.
Okay, great. So that should give people an idea of how it works too, because obviously Oracle RAC is not available for MySQL and Postgres and whatever. Oops.
Right.
Alrighty. Anybody else have any other questions, or? And it's the same with writing. If you write, obviously you can't write to the same data at the same time because it's a shared disk. How do people do backups on your system for, say, disaster recovery? Because there's a lot of, I know in the MySQL community, people end up using something like a SAN, and then the controller dies or the SAN itself dies, and then they're up the creek without a paddle because they didn't have any backups. They just figured the SAN was so robust. How do you recommend doing backups or avoiding that kind of scenario with a shared disk implementation like this?
So the main thing in terms of recovery is that your storage needs to have a mirroring. So if something goes wrong at the storage layer, then the system will cheat and use the mirrored image of the data. Then the system was designed such that there isn't a single point of failure, which means if a node fails, a different node takes over the log file of the node that failed and undo the uncommitted data. So if something like that happens, all the transactions which haven't been completed would be undone by a different node. And then if we've got one node which runs the cluster manager, if that node fails, then the new cluster manager comes up. Other than that, you could use all the MySQL utilities for backup. So you could back up a table and a database in a pretty much way as you would do it with DynaDB. We don't have yet in this version hot backup.
Okay, and but you sounds like you've thought about hot backup and you've got a plan for it?
Yes, but it wouldn't be in the first version. It will be explained for the next version.
Okay, how
Sure.
often? Yeah.
Question.
Yeah.
What happens to the locks if the node fails? Any locks that were required by the node when this failed? They have the recovery log to undo things. But
Right. So the question is, if a node fails, what happens to the locks that it had held before it failed? Particularly if it's a failure, like say a network failure, where MySQL is still running or whatever, but it's just a network failure that it can't talk back and forth. How does it deal with the locks on that?
Right. So that's a good question. So what happens is we've got one node which is maybe I can put on the other machine. Anyway, we've got one node that runs the cluster manager, and this node is aware of all the logs which are being held by all the nodes. So if the node breaks or the communication to the node breaks, then the cluster manager has this information, and so those locks are being held until a different node uncommits the data, the transactions which haven't been committed. And then once that is done, the cluster manager, rather than the node, would release those locks. Did I answer the question?
Yep. Great, and obviously you have this monitor here, which is great, but what kind of, how could you, like if you already have like Nagio set up or Hyperic or something, how could you monitor, like how, is there a special ScaleDB process? Is it a centralized thing? Is it an agent on each node? How does it work to figure out if it's up without using this dashboard or by using some kind of textual command through an existing monitoring system?
Well, the whole thing is very transparent. I mean, you don't do anything different than you would do with InnoDB. I'm not sure I understand completely the question. So let me just say that you take MySQL with ScaleDB and you run it on a particular node. You could use any utility or, I mean, anything that you would use with InnoDB or MyISAM would work with that, because we just get calls to read and write data from MySQL, and everything which is on top of that, and all the tools and the monitoring tools are pretty much the same.
Okay, so I guess the question is, let's say I work at a company and some databases are using ScaleDB and some aren't. How would I figure out which ones are using ScaleDB and which ones aren't? Like, is there a process on the machine, or is there, how do I know that a MySQL instance is either using ScaleDB or not? Just look at storage engines and information schema, or?
There is a ScaleDB code that runs on the machine, like the storage engine. Now with MySQL, you assign a particular table to a particular storage engine. So the typical scenario is that we put a MySQL instance, and there are more than a single engine that is being used at that particular time. So you would see this code running on that particular machine.
So essentially, you look at the engine name, and that's how you.
All right. So I could go to the information schema and say, are there any databases using ScaleDB? The engine, the storage engine, ScaleDB. Okay. And it's a transactional engine.
It's transactional.
Okay.
So within a node, is it just a storage engine, or did they modify any MySQL's optimizer to take advantage of it?
So the question is it just a storage engine, or did you modify the optimizer? And if you're installing it, do you just like plug it into an existing MySQL, or is there a special MySQL download, or?
Just storage.
So we haven't modified the optimizer. It's a storage engine. We haven't done any change to the MySQL code. So actually, you download MySQL from the MySQL website. You download our code from our website, and you make some changes in the configuration files, and then it runs. And the interesting thing is that MySQL, when it runs on a particular node, is not aware that there is a clustered system underneath. So he thinks that it's just a single instance that runs, and all the clustering is done in the storage engine in a way that MySQL is not aware is not aware of the clustering. So that brought some interesting problems that we had to solve, and I can talk a little bit about that if that's interesting. I mean, up to you.
No, I think that's good for now.
So if I were setting up a ScaleDB service, what I would do is I would set up a MySQL server download and install MySQL, and instead of saying for the engine underneath, rather than saying InnoDB or something like that, I would say ScaleDB, and that would sit underneath it.
So the question is, like, let's say I'm going to go and install, you know, a database that has ScaleDB. So I go to MySQL, I download MySQL, and then I go to ScaleDB and download ScaleDB and just use it, and that's how it works, and then change tables to that storage engine.
Right. So when you go to the create statement, you could specify use ScaleDB, like you would say use MyISAM or use InnoDB, or you could put it in the config file that ScaleDB would be your default. And then whenever you define a table and you haven't specified a particular engine, it would be ScaleDB either way.
Okay, great.
It's very easy, very straightforward to install it and then run it. It's very simple. There is one simple init file that you need to add, and it has some basic configuration parameters like the TCP IP that you have to communicate with the cluster manager, and it's maybe 10-15 minutes process, and once you've done that, then you're ready to go. And we'll be able, I mean, if there is someone who is interested to try it and become a beta customer, we'll be happy to let him download and use it, and we'll be happy to help him to configure, make it run, test it.
Great.
Sherry? Do they have performance metrics in the ScaleDB engine?
Do you have performance metrics inside, like you know, in performance schema or information schema? Like, are there any extra numbers that you can get? That's your question.
So the answer is yes. I mean, we've got, when you run the ScaleDB, there is an option, there is a flag that you could use, and that would let you get statistics about the number of IOs and the number of the time that the process takes and which files were accessed and for how long and so on. In terms of performance, there is another very special feature in the engine. We use a very special indexes that provide in many cases, in cases that usually people would do join operations. We have a very unique way to do those joins very efficiently. So in terms of performance, we expect that in many cases we could provide better performance that you would get with regular, compared to regular indexes that are used by other storage engines.
If they didn't change optimizer, how they change that behavior, how they create plan? Say they have to change something in order to provide different plan.
So the question is, how did you provide a different query plan if you didn't change the optimizer? I think there's some query plan stuff in the storage engine itself.
We don't use different query plan. What we do is did you show them the multi-table index? You didn't go. I see. So what we do in terms of the indexing is we can address, we have something which is like materializing the views in a way that, in a virtual way, which means that the index creates the view and the data is can be retrieved from multiple tables and presented to the user if there is a view, a real view that was maintained by the system. And we have a way to do it in a completely transparent way, so that you don't have we don't have to tweak or change the query optimizer. I can show a few slides on that if there is interest.
Okay.
So
do you want to see slides on it?
Yeah.
Do you want to see slides on the indexing or?
Yeah.
Yeah? Okay.
Yes,
so
please.
1 second. So, do you see that screen with the tables?
Yep.
Okay, great. So in a regular database, you use B-tree as your main index structure. And the thing about B-tree is that you've got an index per table. So in this example, you've got an index over table 1, another index over table 2, and so on. With ScaleDB, the index maps not only the data, but also the relationship. So let's say that table 1 is customers, and customer has invoice, which is table 4. The index shows us the relationship between the customer and the invoice, which means if I do a search for an invoice, I would, for a particular invoice, I would get the customer information basically for free. So let's see an example. I have a query here that retrieves the enrollment information, student information, and college information from a particular database. So with B-tree, if I want to see the enrollment of if I want to see all this information relating a particular enrollment, I need to query the colleges separately and the students separately, and the enrollment row separately. Actually, it would be done the other way around. I would start with the enrollment, pull up the enrollment, then bring the student information, and then bring the college information. But every process would be atomic, and then I would have to join those the results for the application, which is my regular join operation, which is expensive since if I have a lot of data, I would need to do a lot of IOs on those indexes and data tables to get the result. With ScaleDB, I can send the query, and with one index that maintains the relationship, I can access the college information, the student information, and their enrollment information, and I would be able to give it to the application. So I get something which is very similar to a materialized view, but without maintaining the view. And if you would try things like that, you would see that the number of IOs that you would need to do in order to satisfy the query is less than the number of IOs that you would do with a regular join operation. So, yeah, so again, I mean, what would be the performance difference depends on your application and the schema and so on, but this is tests that we ran some time ago for querying attribute value pairs in a catalog application, and we tested it against DB2, and we showed that DB2 at some point started to have a serious performance issue, whereas we were able to maintain the pretty much constant performance. So that's kind of a brief overview of our indexing, and there is a lot of information on in our website. If you go to learn more, and then technology, there are white papers that give all the details about how we index data and how queries can run faster if you were to use this indexing approach.
So do you pay a penalty on insert and updates for this kind of indexing approach? It seems maybe contrary to like an OLTP focus.
So the question is so if being better with this indexing, does that mean that there's a write penalty like on insert and update? Because that seems not to jive with the OLT, that it's better for OLTP, if that were the case.
So is the question, do we pay in the inserts because of the indexing?
Yes.
Okay, so the answer is no, and the reason is that the index, there are two properties that help us a lot in terms of performance of updates. One is that the index structure is very compressed, and the second one is the thing which I mentioned where the relationships are maintained. So if we take this example that we've seen, and let's talk this time about insert instead of query. When I want to insert enrollment in a regular database, you would have to make referential integrity checks. You would have to see that the student's information exists, that the college exists, and after those referential integrity integrity test, you'll be able to do the insert. Since we have all the relationships mapped inside the index, we don't have to do, we get the integrity check for free. So you save those lookups, and with a single insert, you've done two things. You inserted a new item, and also you make sure that the integrity is maintained. So this is one thing. The other advantage comes from the fact that the index is very compressed, so you get a better caching ratios and obviously faster to index if your index is small versus the larger index. So I think that you could find advantages in using our indexing structure, not only for queries, but also for updates and insights.
Yeah.
There's no shared cache, so I'm guessing if you commit a transaction, it looks like you have to flush the data to disk.
So the question is, it looks like each node is independent and there's no like global shared cache. So if there's a write on node 1, then it has to actually flush to the disk, and then node 12 would read from that disk. Is that how it works?
Right. Yeah. So we synchronize the info through the disk. The architecture slide. I'll bring the slide, but yeah, the synchronization. So if I updated a block and this block is needed by a different node, then the way it would get it, I would have to write it to disk, and he would have to read it from disk.
Okay. So are there some delays sometime because of that? Because a lot of, I guess the question is, so then do you not have a lot of stuff in a cache? Because with something like, say, InnoDB, you have the buffer pool, which can be very large, and you can wait to write the information to disk until you have, say, 90% of the pages are dirty or something like that. So that doesn't. How does it work with having a lot of stuff in memory too? Because you don't end up, the performance is going to be a lot different in that kind of a case.
Right. So this is a very good question, and it's not a very simple question. I mean, it goes to the first. I mean, it starts maybe from the differences between a shared disk and a shared disk and a shared nothing architecture. So if you are if you are able to work in a structure where everything is executed in a particular node, then why go to a cluster environment, right? I mean, it creates an overhead of synchronization things between nodes. But we started from a point where shared nothing is not good enough. It's not good enough because it limits you to the capacity of the particular node, and you could go beyond that. Now, if your application is doing a lot of contention, so let's take an example where all the users are trying to update all the time a particular block, then going to a shared disk is a bad solution. I mean, even Oracle, not just ScaleDB, every shared disk system that has a lot of collision between all the nodes all the time wouldn't provide you a great performance.
And that's fine. I mean, you can't have everything. It's perfectly okay to say that this is for needing to be able to access the data from many points, and it's not it's not the fastest thing in the world. That's okay. I mean, we're just trying to get a sense of what's the sweet spot for this for ScaleDB.
So yeah, so then, like I said before, it's very hard to define rules. You have to take your application and try it. And in most cases, I would say that we could provide you out of the box great performance, great scalability. If the application would be such that all the nodes are trying to hit all the time the same blocks, then that wouldn't be the best way to scale.
And what motivated you to make this product in the first place, right? Obviously, it's great to say, okay, well, you know, we don't need to set up a replication slave and do all that work. Does it help, like, does it help in cases where there's so much writing that the slave can't keep up? Like, what are the cases in which it helps? And why use, say, ScaleDB rather than a SAN?
Right. So the motivation was that people, on the one hand, in terms of the usage of the open source databases, there were so many people that built applications on the open source databases, but the perception was that those open source databases are good for just particular types of applications, like read-mostly type of applications, and you don't see it go into OLTP and other more heavy-duty types of applications. So that was one thing that triggered to develop the engine. From the other hand, we were, it was being Vernon, we had very interesting technologies in terms of indexing and in terms of clustering, but we didn't want to build a new product. We didn't want to say, well, there is a new database and deal with that. So the fact that the idea was, why won't us wrap those technologies in a way that could be pluggable to many environments or to many different databases or applications. And so that's how the idea of ScaleDB moved to be something that is a real product that is working underneath. Currently it's MySQL, but the intention is to have APIs to other environments and other types of applications.
Okay.
I'm not sure that I answered your entire question. Maybe I left something.
No, I think that was good. So is that it? Do we have any more questions? Great. Well, thank you so much for.